once the reactants are combining, it forms an intermediate stage. Okay, it forms an intermediate stage which is highly unstable. So what are spontaneous and non-spontaneous reactions? Spontaneous reactions means they will happen on its own. It does not require any external force for the reaction to take place. According to a particular direction only, they can come and collide with each other. So for example, let us take the formation of methanol from bromoethane depends upon the orientation of reactant molecules. Hello everyone, this is Ambli Unnikrishan from the Department of Chemistry, Vidhyaashram School of Excellence, Mysore. So today we are back with session 6, the last session of the chapter Chemical Kinetics. So in the last session, we studied about the temperature dependence of the rate of the reaction, right? So we studied that when the temperature increases, the rate of the reaction also increases, right? And then we studied one important equation, that is Arrhenius equation, that is the equation which is relating between the rate constant and the temperature. Right, and we studied what is activation energy as well as qualitative increase in reaction rate with temperature. Okay, so in today's session, we are going to study about the effect of catalyst on a rate of reaction. So we have already studied the dependence of concentration on the rate of reaction as well as temperature dependence on rate of reaction. So the last one is effect of catalyst. How the addition of a catalyst will vary the rate of the reaction, and collision theory of chemical reaction. We need to study what is collision theory and what is effective collisions, and then we'll do some numericals as well. Okay, so beginning with effect of catalyst. So how does the rate of the reaction vary when a catalyst is being introduced into the reaction? Let's see. A catalyst, first of all, what is a catalyst? A catalyst is a substance which alters the rate of a reaction without itself undergoing any permanent chemical change. Okay, so a catalyst is a substance which is added to a chemical reaction to increase the rate of the reaction or else to alter the rate of the reaction. But the speciality of this catalyst is that it does not take part in the chemical reaction. That means it just alters the rate of the reaction. Once the reaction is completed, along with the products, you will be obtaining the catalyst as well. That is, it does not undergo any chemical change in the reaction. Okay. So for example, if you are taking this particular reaction, 2 moles of KClO3 reacts with manganese dioxide, MnO2, and forms 2 KCl and 3 O3. Okay, so manganese dioxide is used as a catalyst here, which increases the rate of the reaction. Okay, so how is actually the reactants combining and finally forming the product, and how is the effect of catalyst here? Let us see. So that let us understand using intermediate complex theory. That means once the reactants are combining, it forms an intermediate stage. Okay, it forms an intermediate stage which is highly unstable. Okay, and from the intermediate state, further the products will be formed and we will obtain our catalyst back. Okay, so according to this theory, a catalyst participates in a chemical reaction by forming temporary bonds with the reactants, resulting in an intermediate complex. Okay, so the reactants will combine with each other as well as it will combine with the catalyst and form an intermediate complex. Okay, so this intermediate complex will be unstable, and what happens? This has a transitory existence, only it will exist for a small period of time and it will further decompose to yield products and the catalyst. So what happens? The catalyst will react with the reactants. Yes, it will form temporary bonds with the reactants and form an intermediate stage. Okay, intermediate complex. From there, further the products will be obtained as well as the catalyst will be obtained back. Okay, so I hope it is clear. Now, let's see, the catalyst provides an alternative pathway or reaction mechanism by reducing the activation energy between the reactants and products and hence lowering the potential energy barrier. So we have already studied what is activation energy. So activation energy is the energy required by the reactants to form an activated complex. So we have even studied this graph, right? Potential energy versus reaction coordinate. This is your reactants and here is your products. Okay. So the energy required by the reactants to reach here, that is to form the activated complex, that energy is called as activation energy. Right. So when we are using a catalyst, how exactly is the rate of the reaction is getting increased? What is happening there? See, when a catalyst is being added, this catalyst will help in decreasing the activation energy. That means it reduces the activation energy between reactants and products. It forms an alternative pathway. So this bold line you can see, that is the energy of activation when there was no catalyst present. Now this dotted line you can see, the next one, that is the reaction path when a catalyst is added. So as you can see, once the catalyst is added, this is the activation energy. So you can see the activation energy has decreased from here till here. Okay, so now only a little amount of energy is required for the reactants to form the intermediate state, and further it will form the products. Okay, so what is actually the use of this catalyst? It will decrease the activation energy or reduces the activation energy by forming an alternative path. So instead of this path, now the reaction will follow this path, hence the activation energy decreases. Easily the product will be formed. Okay, so hence what happens? Easily the product is formed means the rate of the reaction also increases. So in general, we can say the addition of a catalyst will increase the rate of the reaction. Okay, so I hope it is clear. So now let's see some characteristics of catalyst. Okay, so a small amount of the catalyst can catalyze a large amount of reactants. Okay, so if it is a very big reactant or a large amount of reactant is present, or if it is a very complex reaction also, a very small amount of catalyst is only required to catalyze the reaction. It's not like you have to add in a lot of catalyst. A small amount can catalyze a good amount of reaction, right? A catalyst does not alter free energy change of a reaction. You have already studied what is delta G in class 11, right? So it does not alter the free energy change of a reaction. Also, it does not alter the enthalpy change. That is no change in delta H as well. Okay, so the fourth one, a catalyst can catalyze a spontaneous reaction but does not catalyze non-spontaneous reaction. So what are spontaneous and non-spontaneous reactions? Spontaneous reactions means they will happen on its own. It does not require any external force for the reaction to take place. But non-spontaneous reaction will only take place in the presence of some substance, or it has to have some external force or external source for the reaction to take place. So this catalyst can only alter the rate of the reaction. Okay, it does not help in starting or initiating a reaction. Hence, it alters or catalyzes the reaction which are spontaneous only. It does not catalyze the reactions which are non-spontaneous. Okay, that means your catalyst cannot initiate a reaction. It can only alter the rate of the reaction. Right? Next one is a catalyst helps in attaining the equilibrium faster. That is, it catalyzes the forward as well as backward reaction to same extent so that the equilibrium state remains same, but it is reached earlier. So that is also one application of catalyst. It helps in attaining the equilibrium faster. Okay, so what you have to remember, it cannot initiate a reaction. It just alters the rate of the reaction, as well as there will be no change in delta G or delta H due to the addition of a catalyst. It just alters the rate of the reaction. Okay, and a small amount of catalyst can catalyze a large amount of reactants. Okay, so I hope it is clear. So now moving on to the next one, that is collision theory of chemical reactions. Okay, so according to this theory, the reactant molecules are assumed to be hard spheres, and the reaction is postulated to occur when molecules collide with each other. So as the name suggests, collision theory. So how is that the reactants are combining and forming the product? So what happens is, in or according to collision theory, your reactants are considered as hard spheres. Okay, it is considered as hard spheres, and the spheres will collide with each other. The spheres will undergo collision with each other and form the products. So what you have to understand is, all the collisions will not result in the formation of product. So once we studied the characteristics of the collision theory, we'll understand that. So let's see. The number of collisions per second per unit volume of the reaction mixture is known as collision frequency, which is represented by Z. So the number of collisions, okay, it is the number of collisions per unit volume per second of the reaction. Okay, so for a bimolecular elementary reaction means it is a single step reaction. Okay, so for a bimolecular elementary reaction, bimolecular means the molecularity is 2, right? And elementary reaction means it happens in a single step. So A plus B is giving the products. So now the rate of the reaction can be written as, yes, rate is equal to ZAB. Now what is Z? We studied now collision frequency. ZAB into E raised to minus EA by RT. So this reaction, this equation we have already studied, which is the Arrhenius equation. So this equation we have already studied, which is the Arrhenius equation, to which the collision frequency is also included, that is ZAB. So the equation becomes now rate is equal to ZAB, which is the collision frequency into E raised to minus EA by RT. So what is EA? Activation energy, R is universal gas constant and T is temperature, which you already know. Okay, so the collision frequency will be also included here. So where ZAB represents the collision frequency of reactants A and B. And E to the power E minus EA by RT will represent the fraction of molecules with energies equal to or greater than the activation energy. So E raised to minus EA by RT will actually represent the number of molecules which is having energy equal to or greater than the activation energy. So comparing with the Arrhenius equation, we can say that A is related to collision frequency. So if we are comparing these two equations, right, the Arrhenius equation was rate constant is equal to A into E to the power minus EA by RT. So if we are comparing these two equations, we can relate ZAB as well as A, that is collision frequency and A, right? So and all collisions do not lead to the formation of products. So as I told in the beginning, all the collisions, okay, will not result in the formation of products. Then what type of collisions will result in the formation of products? It is only effective collisions which will lead to the formation of products. So let us understand what is effective collision then. Okay, so effective collisions are those collisions which lead to the formation of products. Okay, and the number of effective collisions is governed by the following two factors. It is one is energy barrier and next is orientation barrier. Okay, so as I told you, according to the collision theory, the reactants are considered as hard spheres which will collide with each other and form the products. And also all the collisions do not result in the formation of products. It is only the effective collisions which will result in the formation of products. Okay, and it depends on how we can say whether it is an effective collision. It depends on two factors, that is energy barrier as well as orientation barrier. So what is energy barrier? The collisions are effective only when the molecules possess energy greater than or equal to threshold energy. So threshold energy is the minimum energy, right? So if the reactants is possessing this threshold energy, that is a minimum energy required, then only the reactants will collide with each other, or we can say that then only effective collisions will take place and the product will be formed. So first one is energy barrier, that is the reactant molecules must have a minimum threshold energy. Okay, so that minimum energy is required, then only effective collisions will take place. Next one is orientation barrier. The reactant molecules must collide with favorable orientation in order to facilitate the breaking of old bond and formation of new bonds. So that means in random directions, the reactant molecules can't collide with each other. That has to happen in a proper direction itself. So that is what is orientation barrier. Okay, see again, it must collide with favorable orientation in space. According to a particular direction only they can come and collide with each other. So for example, let us take the formation of methanol from bromoethane depends upon the orientation of reactant molecules. So as you can see here, bromomethane is taken here which reacts with OH minus, and if it has to undergo effective collision, if these two reactant molecules have to undergo effective collision, it has to happen in a proper orientation. That means, see here, what is the reaction that is supposed to happen? That is, the Br minus will leave and OH minus should get attached to the positively charged carbon. Okay, so this is what is the reaction which is supposed to happen here. So what happens here according to the proper orientation? What will happen? See, if the Br minus is leaving from here, this bond will start breaking. This carbon-bromine bond will start breaking, and the OH minus should be attacking the carbon atom from this direction. Okay, so see, in the improper orientation, your Br minus is here. So your OH minus cannot come and attach to carbon in this direction, because bromine ion is already present here. Bromine is already there. So OH minus cannot come and attack from this side. So if this has to leave, the attacking reagent should come and attach from the opposite side. Hence, you will get your alcohol and Br minus. So in this case, as the orientation is not proper, it is an improper orientation, no products will be formed. Hence, the orientation is also important. I hope it is clear. So, the proper orientation of reactant molecules lead to the bond formation, whereas improper orientation makes them simply bounce back and no products will be formed. Okay, that means if the OH minus is attacking from this direction, yes, you will get the product which is required. But if it is attaching from the same direction, if it is trying to attack from the same direction, the orientation is improper, hence you will not get the product. Okay, now to account for effective collision, another factor which is P, called as the probability or steric factor, is also introduced. So after studying about the collision frequency, we introduce ZAB here. Now after the proper orientation as well as energy, we have to introduce this factor as well, that is P, which is called as the probability or steric factor. So finally your equation for rate becomes rate is equal to P into ZAB, which is the collision frequency, into e to the power minus EA by RT. Thus, in collision theory, activation energy and proper orientation of the molecules together determine the criteria for an effective collision and hence the rate of chemical reaction. Okay, so according to collision theory, yes, effective collisions has to take place, then and then only the product will be formed. So for effective collisions to take place, yes, they should have a minimum energy. Yes, there should be collision frequency as well as the orientation must be proper. All these factors are important in the case of collision theory. So I hope collision theory for the formation of products is clear for you. So now let's move on to some numericals based on what we have studied. So the first question is the rate constant of a reaction at 500 Kelvin and 700 Kelvin are 0.025 second inverse and 0.075 second inverse. Calculate the value of activation energy. So we have studied this equation. When there are two rate constants given and two temperatures given, we can directly use one equation. We have studied that equation, that is log of K2 divided by K1 is equal to EA by 2.303 R into T2 minus T1 divided by T1 T2. So this equation we have already studied. So in this question, K1 is given as 0.025 second inverse. Yes, so from the unit, can you tell me which order will be this reaction? This will be a first order reaction, right? And K2 will be equal to 0.075 second inverse, right? And T1 is given as 500 Kelvin, which is also given in the question, and T2 is given as 700 Kelvin. So these values are already given. So you can directly substitute it, and R you can use at 8.314, which is universal gas constant, which is a constant value. Okay, so you can directly substitute in this equation. What is that you have to calculate? EA, right? So log of what is K2? It is 0.075 divided by 0.025, right? Log K2 by K1 will be equal to EA divided by 2.303 into, what is the R value? It is 8.314 into T2 minus T1. What is T2? 700. 700 minus 500 is 200. Yes, 200 divided by 700 into 500. Right. So this is the equation. So once you do the log of this, you'll get 0.544, which is equal to EA into 5.314 into 10 to the power minus 4 divided by 19.5. So once you solve this part, you will get this answer. So this 0.554 is the log of this part. So now just by rearranging this equation, what is that we have to calculate? It is EA, right? So how can I write EA? It will be equal to 0.544. So divided by 19.5, if I am taking to the other side, it becomes multiplied by 19.5 divided by 5.314 into 10 to the power minus 4. Right. So after solving this, the energy of activation will be equal to 18230.8 joules. Okay. So this will be the answer, energy of activation. So you have to directly substitute in this equation. So moving on to the next question. The first order rate constant for the decomposition of ethyl iodide by the reaction is given here at 600 Kelvin is 1.6 into 10 to the power minus 5. So K1 is given as 1.60 into 10 to the power minus 5. And at what temperature is this K1? It is 600 Kelvin. Okay. Its energy of activation. Energy of activation is also given. That is 209 kilojoule. It is also given. Now calculate the rate constant for the reaction at 700 Kelvin. That is, we have to calculate what is K2 and temperature is given as 700 Kelvin. So the difference from the first question is, in the first question, energy of activation you have to calculate. EA you have to calculate. In this question you have to calculate K2. Right. So again the same equation we are going to use here. That is log K2 minus log K1 will be equal to EA divided by 2.303 R into T2 minus T1 divided by T1 T2. The same equation we are going to use. Okay, instead of taking log K2 by K1, I just took log K2 minus log K1. Log A minus log B will be log A by B itself, right? So K2 is what we have to find. Okay, so we keep it as it is. Log K2 will be equal to, what is K1? Yes, log of, if I am taking this to other side, this becomes positive, like log of 1.60 into 10 to the power minus 5. Okay, and this plus EA, which is already given in the question. So it is 209 kilojoule per mole. So kilojoule we are converting it into joules. So it becomes 209000, right? Kilojoules into joules divided by 2.303, again R we are considering 8.314 into T1 and T2 is already given in the question. T1 is 600 and T2 is 700. So 700 minus 600 is 100 divided by 700 into 600. Okay. So continuing this, log K2 will be equal to log of this, log 1.60 into 10 to the power minus 5 is equal to minus 4.796. Okay. So the log of this is minus 4.796 plus, once you do this calculation, you get the answer as 2.59. 2.59. So log K2 will be equal to, minus 2.197. That is the minus 4.796 plus 2.59, you will get minus 2.197. So how do you calculate K2? K2 is this value. So log K2 is minus 2.197. So K2 will be anti-log of minus 2.197. Right? So that will give you a value, that is 6.36 into 10 to the power minus 3 second inverse. So this is the K2 value. So from the same equation, instead of writing log K2 by K1, I took it as log K2 minus K1, log K2 minus log K1 and substituted the values here. So just by simple calculation, you can find the K2 here. Okay. So I hope the numericals is also clear for you. So by this we come to an end to this chapter. So I hope the topics we have discussed in this chapter is clear for you. So in the next session, let us meet with a new chapter. So that's all for today. Thank you.